All right. All right. So, is the mic working? I am not hearing it. Is it working? Can you hear it in the back? Hello. Okay. Okay. Yeah, it's working. All right. Um, huh. It sounds different today. Okay. Well, hopefully, if you're watching a recording, hopefully you could turn up your volume or something. I'm sorry. Okay. Yeah. So today's the second lecture in this section of 364. One quick announcement. I know a couple of people joined late, and like for Piazza and for Piazza, you have to I have to manually add people. So if you joined late and you're not added to Piazza yet, ping me, like just email me and I'll add you to Piazza. Um, Canvas should be fine. Piazza is probably not fine. Prairie Learn, you should be able to add yourself. So if you have any access difficulties, ping me. That's the moral. Okay, so let's see. So today's lecture is on PyTorch storage, indexing, CPU, GPU data types, and functions. So last time, if you'll recall, we went over a brief introduction to PyTorch. You know, that whole AlexNet example. That's our goal towards the end of the semester, to be able to write a deep neural network without too much difficulty fairly quickly in PyTorch. And so that's roughly the skill level you need. That's approximately the skill level you need for interviews. So if we get there, should help everyone out. So we introduced ourselves to tensors, and now we are going to continue on with tensors, talk about indexing, and then we are going to talk about functions and just sort of using PyTorch to view the computing pipeline. And then next week we'll do a brush up on linear algebra, and then we can finally start doing some auto gradients and regression stuff. All right. So yeah, advanced slicing and indexing, common activation functions, multi-functions derivations, and computation graph. So, by the way, all misspellings are intentional. I am going the Trump route and being like, whatever is on the screen is totally intentional. Let's see how that works. Okay, so, tensor storage. Let's talk about tensor storage first. And then all of you have taken 220 already. And recall that there is a memory hierarchy in every computing system that works together to deliver as much data to the processor as fast as possible. I am seeing a red flickering, so everyone else is seeing that too, right? Okay, let me just, this is getting a little annoying. Wait, did it work? No. Oh my God, okay, one sec. Let me try. Alternate. All right, any red flickering? No, perfect. All right, so, okay, so everyone here has taken 220? Okay, I thought I saw some. And we know that there is a memory hierarchy at work, that we need to get data into the CPU, into a processing unit. We have GPUs now. We have tensor processing units also. So we need to get data into a processing unit, but we know our processing units are small because they need to be fast. And yet, getting all that data into that small space is a difficulty, right? So we have a hierarchy at work. Mainly, we have registers that are close to the processing units, that are close to the ALU, that can be accessed within a cycle. And given that modern chips are run at a couple gigahertz speed, the fastest memory runs at about tenths of nanoseconds, right? So we have those registers, and then we have multiple levels up. We have caches that exist on the CPU that give you more space, allow you to store more data, but also it comes at a cost. They're slower. And then we have RAM, both in the CPU and GPU space, where again, we could store more data, but you have to cross the DDR bridge in order to get to that data. So that's again a latency penalty. And then we have hard disks, which are another which can store even more data, but again, it's another latency issue. And then finally, even though it's being slowly phased out, there still do exist tape drives in server farms where you could store a large amount of data, but they're also incredibly incredibly slow. So this is more for data that you will rarely, if ever, access, but you don't want to lose. And then as you go, you have data that you sometimes access but don't need immediately. You could store it, and then when you want to access it, this data gets transferred to the RAM. The RAM data gets transferred to cache. Cache data gets transferred to the CPU, and so on. Oh, that should be CPU registers, not RAM. Okay, small typo there. Okay, so the point of this slide is that there is an inverse hierarchy between size and latency, right? So, or actually, size and latency are closely correlated. Let's say that. Size and latency are closely correlated, but latency we want as small as possible. Size we want as big as possible. So you get a nice little curve there, right? So that's the issue, and the issue is especially pronounced when you are dealing with modern AI applications that have just become increasingly larger. I don't think OpenAI reveals this explicitly, but their models are well into the trillions of parameters large. And so the question is, when you're developing a data-intensive computing application, or the data includes both the training inference data, but also the model data, all the weights that the model has. The question is, where is the data? How do I get it there? Does all the data fit into machines at once? Do I need all the data to fit in a machine at once? You could, in theory, train a large model on multiple GPUs, as most large companies do today, but that is hard to get working, to get the training process working on multiple GPUs. You need a lot of advanced computing techniques to do that. And can you load all your data into the CPU? Or could you load all the data into the GPU RAM? And again, that's a big question. Most of the larger models of Hugging Face, you can't even load them all on a single GPU, which is a hard thing, right? So there's no general answer. You just got to play it by ear. But we have to be aware of the constraints. And more importantly, we have to try to be as conservative with our data as possible. We can't afford to waste anything. Okay, so this is actually computing is almost cyclical, because I remember about 20 years ago when I first learned computing, everyone was learning C, and my computer science professor sort of beat into me the importance of freeing your memory at the end of every program, because the compiler back then didn't automatically do this. It wasn't as optimized as it was today. Then fast forward, college, 10 years later, Python comes along. No one cares about memory anymore. And memory is effectively free. Scripting languages take dominance. People don't care about memory anymore. And now, 10 years later, we're back to, oh man, memory, we've used too much. And now we have to be conservative with memory again. So, nice little, you guys, hopefully you guys, in another 10 years, we won't need to worry about memory anymore. And all the models fit in a small CPUs. But in the meantime, we have to be concerned. Okay, so talking about memory, let's continue our discussion on tensors. And last time we talked about strides and tensor views versus actual memory allocations. And so this time, let's continue on with that and talk about contiguity. So as we remember, every tensor is stored in a torch.storage container. This is just one struct inside the tensor object, and this contains a data pointer, a CPU pointer, or a CUDA pointer to store the data in the GPU RAM. It's the number of size, the element size, and the strides, right? And so we know with these things here, we could store most dimensions, most tensor dimensions in a contiguous block of memory. And having it all in a contiguous block of memory is actually a wonderful thing because it allows us to run things as fast as possible, right? So as an example, we can initialize a random torch tensor like so. Let me zoom out. There we go. We can initialize a random torch tensor, and we could actually test if the tensor is contiguous. There's a nice little helper function that by PyTorch that allows you to check if the memory is contiguous and check what the size of the memory is. To shape the size. There we go. And yeah, what the size of the memory is along the first dimension and of a. Might as well fix this. I'll re-upload it later. And where A is stored. And also, if we want to put A in the CPU, we know where it goes, where the data pointer is. I mean, when we initialize it by default, Torch assumes you want to put the data in the CPU. So that's why B is also stored at the same location. And also, you could use some helper functions. For instance, you could use the exponential functions to change around the data and have C stored at a new location, like so. And therefore, so we do various operations and we get various things. One quick question. Quick question before we move on. Sorry. Why is C not a view? Just checking if you're awake. Why is C not a view? And this is an incredibly stupid question. So this is yeah.
Because the ext function
Yeah, you're changing the data, right? Yeah, okay, just making sure. Yeah, you're changing the data. We still want the A is still there, right? So we still need the original data. So we're changing the data here. So therefore, this right here reallocates a new block of memory with exponential of the values in there. Good. And also remember that B is actually a view of A. We know this because the two data pointers are exactly the same. Since they're exactly the same, we know that when we said B is equal to A.CPU, it didn't allocate a new memory. Instead, PyTorch said, well, do we really need to allocate a new memory? Instead, I'll just allocate a new wrapper and have that wrapper point to the same data as A, and therefore, that's what this is showing. So B is a view of A, and so when we change the value of A11, we set it equal to 0. The value of B11 is also equal to 0. Okay? So that's the concept of views. And so some more examples. For instance, if we initialize a tensor, A, a 3x3 tensor, A, that contains the values 0 through 8. Then we could do some nice advanced indexing, the same type of indexing we do with NumPy arrays, and take a subset of that tensor. For instance, if we want these values right here, we could simply say B is equal to A 1, 2, 3, 1, 2, 3, not containing 3, and 1, 2, 3. Right? So that makes sense, right? I think that's reasonable. So, the one major thing to discuss, to point out right now ahead of time, and we'll discuss this more, is that pretty much every sort of slicing operation you could do in NumPy, you could do that with PyTorch tensors also, right? PyTorch is pretty much has stolen a lot from NumPy. Not stolen, borrowed, generous, borrowed with great affection. So everything you could do with NumPy, pretty much that functionality is built in tensors also. Yep, come on. There we go. So is B a view of A?
No.
No? Why not?
Because they're different sizes.
They're different sizes. That is true. They are different sizes. But we do know that views could be smaller, right? We could, for instance, have, let me see if I could, no, let me, B. Okay, there we go. I could, for instance, I could say C is equal to a, what was I going to make? Oh, comma 1. I don't know. Print C. Oh, that's from later. There we go. So print C. So that makes sense. So if I do, what was the dot data pointer? There we go. I was not. So I want to print a dot data pointer. Okay. And C dot data pointer. They do look to be, oh, they are different. Wait, are they different? Yes. Oh, well. Well, let me do a sanity check right now. A dot 3, oh, not 2, 2. It's equal to 0. 2, 1. A 2, 1. Oh, maybe it is different. Oh yeah, no, they are a view of each other. So they are a view of each other. So we do a small test. So if since A is smaller than C, if C was larger than A, let's say C was equal to A repeated, then I would totally agree with you. So it's the pigeonhole principle, right? You can't fit more memory into a smaller space, so you have to reallocate, and pretty much whenever TensorFlow has to reallocate memory, it just reallocates the entire block. It doesn't when you have to reallocate memory, like you can't reallocate it in place because then you have to make sure the neighboring memory is not being used and all of that sort of thing, right? So, it's still possible that B is a view. Well, B is smaller than it, so in theory we could still fit the data that B is referring to. It's still fittable in original A, right? So what do we think? So have I ruined your confidence in your answer? Yeah, I mean, it's still possible B is not a view of A. That doesn't disprove this hasn't disproved anything. But I just wanted to sort of get that sort of thought process out of your head, that just because the two memories are not the same, the one can't be a view of the other. Yeah?
I think it's possible that B is a view of A, and you would do that by setting B's data pointer to the element 4, or the address of element 4.
Okay.
And the stride in the x direction is 1, and stride in the y direction is 2.
Okay, interesting. So that would be an interesting way to do it. So instead, if we wanted to represent B, we could use a little bit of computing intelligence, or like just some pattern recognition, and be like, okay, since we only want this subarray, then we just point the data to this point at 0, and then We point the data to this point at 0, and then we just have the stride in this direction equal to 1, and the stride in this direction equal to 2. And that should take care of most things, right? Let's see what it actually does. Come on. All right, come on. Oh, there we go. So, little same storage helper function I wrote there, because of course when I'm just looking at the data pointer, it gets a little misleading, because as you just saw, the offsets need to be accounted for. But the point of all of this is to say that, yes, B is a view of A. So even though B is a subset of A, it is a view of A. Okay, that seems pretty reasonable, right? Seems pretty reasonable. By adjusting the strides, you could do a lot. You could pick out a subset of a tensor, and you don't even need to reallocate any new memory, which is kind of cool. And the algorithms that go behind of this are actually kind of fun to look at, and they're not too hard to understand. So if you guys ever have questions about that, there's some good resources. I think there was a blog post I linked in the last lecture that you could look at. Anyway, so is B contiguous? Yes, all the way in the back. No? Why not? Yeah, I would. Well, what do you think? What do you think?
I don't think so, because in memory, considering the way A is set up, it's probably like 4, 5, 6, 7, 8
Yeah,
in order.
yeah.
So like 4, 5, then it skips to 7. So it's not contiguous.
That is true. Yeah, that's the major apprehension here, right? That because in memory, when we allocated A, you imagine that when A was allocated, the memory will go from 0, 1, 2, 3, 4, 5, 6, 7. And now you have B, which is going 4, 5, and then 7, 8. You imagine there's a 6 that's being omitted, right? So we could actually check. There is, again, helper function that checks. B is contiguous, and actually you're absolutely right. It is false. And so you guys didn't fall for the trap that I was hoping you would fall for to generate some instructions. To me, this looks very contiguous, right? The first time I tried using PyTorch, I was like, why wouldn't it be contiguous? Because it's just this one block of memory. But again, as you guys correctly ascertained, you're going from this is a two-dimensional structure, and memory is always a one-dimensional structure, right? A memory is just one list. So because of that, we have a 3D structure, and we could represent it as a list of memory, but really what it comes down to is, and it would have been nice to actually match the code. That was dumb, but the point remains that when we get to B, we don't need to allocate a new memory. The strides take care of everything because we just point the data pointer here. Stride of 1 in this direction, and stride of 2 in this direction, right? So everything works. But, oh, stride of 3 in that direction. So there is a mathematical way to make the strides work in the sense that you won't need to allocate new memory. So that's good, but the issue is that the memory is no longer contiguous. So the question now is, does it matter? Does contiguity matter? So does contiguity matter? And I tried to set up a quick experiment here, where let's get two tensors. One is contiguous and one is not contiguous, and just test how fast we could do math operations on them. Okay, so let's just generate a random tensor, and let's next generate a non-contiguous tensor. And the one way to always reliably generate a non-contiguous tensor is to simply do a data transpose. That's because if you flip the rows and columns, then when you iterate through the rows, you're jumping a lot of spaces, right? So when you take the transpose of a piece of data, you're losing contiguity. Okay? Now, is that an issue? Maybe, maybe not. But we could test that. We're going to test that out by basically taking this non-contiguous vector and creating a new tensor that is contiguous, and that's very easy to do with this nice little PyTorch helper function, whatever, the tensor dot contiguous. Okay, so dot contiguous right here. What this is doing is actually reallocating more memory. Okay, when you're transforming a non-contiguous tensor into a contiguous tensor, how do you do it? There's only one way, right? You have data that's non-contiguous, and you need to force it to be contiguous. I mean, there's no other way than to create a new block of data and make sure all the data appears contiguously in it, right? In that new block, right? So this is what this helper function is for, contiguous. And then all we want to do is matrix multiply the non-contiguous vectors together and matrix multiply the contiguous tensors together and see what we get. And so if we do this little experiment, we see that we get a small but definitely noticeable slowdown if we're for non-contiguous vector spaces. So in this case, we have a approximately 20% slowdown. In this case, we have, so this takes 0.1, a hundredth of a second. This takes 12 thousandths of a second. Okay, so is it the end of the world? No, no, it's not the end of the world. But if we scale this up, to a massive machine learning model, suppose you're doing something with millions, trillions of parameters that could all either be contiguous or not contiguous, you know, things that take days to train, that 20% could be the difference between getting your thing done within the next 24 hours or waiting another 24 hours or having a week shaved off your training time or so on, right? So 20%, in this case, it's not, 20% isn't especially significant in this case, but in a case where you're dealing with massive models, it could be significant, right? So one of the things that you should be, so again, speaking of data and being careful to track where your data is, also be careful to track how your data is represented if it is contiguous. It's always better to have contiguity, right? Of course, it comes at a cost because you have to allocate a new memory block when you force the data to be contiguous. So, pluses and minuses. Machine learning is almost an art at this point than science. Okay. Any questions? No? Everything seems reasonable. All right. So now let's. We touched upon it earlier, but let's talk about indexing. Let me put this on Do Not Disturb. Yeah. All right. So indexing. Indexing. So let's talk about basic indexing. We got a torch. We got a torch tensor, and we want to take a slice of it, as we saw in one of the earlier examples. So that's pretty simple. We take a slice of B. We take what do we take? We take the 2 rows, the 1 and 2, and we take the 1 column. 1 and 2, 1 column. That would be that. B is equal to this matrix here. Yep, that makes sense. A 2 by 1 matrix. Yep. So, and also we could manipulate, if we manipulate the data in B, we also manipulate the data in A as well, right? So all that makes sense. Actually, this is probably a good example just to remind you guys that it works both ways. It's not just if we manipulate A, B changes also. If we manipulate B, A changes also, right? So they share the same data space. Okay, so you could effectively say they're both views of each other. That's why in PyTorch, I don't think there's any function that says is there like tensor dot is view, because is view is a relative thing, right? Everything can be a view of each other. So really the only way to see if something is a view is just to see if 2 tensors share the same data storage. And that helper function I showed you earlier helps you with that. Let's see. So if we have a new 10 by 10 tensor, we could we could take every other row and every 3 Yep, and every 3 columns between 1 and 5. And so a little bit of advanced slicing here. And of course, if we change, the value in B, let me print A again. That might be good. We also see that the value in A changes as well. Okay. No. For also, if we print A, oh, I did that there. We changed the value in A also. Okay, good. So, also, if we look at the storage for both, again, we see that they have the exact same data pointer. So it makes sense that they would be views of each other. Okay. Advanced indexing. All right, so I mean, I can't go through all of slicing and indexing in this lecture. There's actually like the amount of like cool little indexing stuff people come up with Python is pretty nuts. So I mean, the NumPy documentation has a lot of good examples on indexing, but just a couple more that are maybe a little interesting. For instance, we don't necessarily, not everything has to be spaced out evenly. We can index based off taking some random rows. These are, to take some random rows and take the 1 and 4 column from each of these rows. So take the 1 and 4 column from row 0. Yep, 1, 4. Take the 1 and 4 column from row 1, 11, 14. That makes sense. 1, 4 column from row 3, 31, 34. Yep, makes sense. So all that indexing works. I think all that is reasonable. Oh, let me minimize that. And if we look at the data pointers, we get the data locations for the various tensors that we defined based off each other. So alertness check is B a view of A? Yes.
Yeah, we're just taking like vertical images of sense of it, so we can always use some kind of offset to make it look.
Okay. I mean, I like the logic. It's just a subset of A, right? So we should be able to we should.
Actually, no, because the offsets are inconsistent.
Okay.
You're making random selections of the rows, so I don't know how you would come up with a formula for it.
Okay, so that's the issue, right? So the issue right here is that in theory, B has less data than A, right? So it seems like maybe we could like the previous examples, we were able to create a view out of A because we only needed a subset of A to form a new tensor, right? But the issue here is that these are just effectively random numbers, right? So the stride is a single number in each dimension, right? So if we have a stride, so the question is, what would the stride in the 0th dimension be here? There's no single number that could represent this mess, right? This is just a bunch of random rows. So because of that, B can't be a view of A. And in fact, if we take a careful look at the data pointer right here, we see that the data pointer is very different between A and B, right? It's not even an offset. It's just a significantly different data pointer. And so that B is definitely not a view of A. And also, the one other reason I put this in the slides is because I was looking at this at 2 in the morning the other night, and I looked at this and I was convinced these two data pointers were the same because I was only looking at the first couple numbers, and I spent literally an hour at like 1 in the morning being like, how could this be possible? Why is how is B a view of A? How is this working? And I Googled, like, how do you slice how do you represent random slices as strides, like a good, like 20 times. I asked OpenAI. I was going nuts. But then eventually I looked deeper and I'm like, oh, they're not the same data pointer. All of this is to say that don't do what I do. Don't do what I did. Build helper functions. Build GUIs that don't force you to look at raw data with your naked eye, because that's almost guaranteed to screw you over sometime. Okay. So that helper function same storage, I highly recommend using it. Anyway, I thought that you guys might fall into that trap too, but it's good to see you today. Okay, so new example. A is again 2D tensor, 0 to 100, 0 to 99, sorry. And we just want, well, let me ask you guys something. What is B? What would B be in this case? Jesus, what would the tensor be be in this case? I don't know. I can't think of another word. Any ideas? Yes.
It would just be like a line of pulses of like, 0, 10, 20, 30, just all of that, just false because it starts with 1.
It would all be false?
Actually, wait. No, only 20 would be correct.
Only 20? Okay, yeah. So, yeah.
Like 20.
Yeah, you caught yourself. Okay, good. So yeah, basically it would just, it's taking the first column of A and just checking if each one is equal to 20, which only one of them is. Only the value at index 2 is equal to A, so there's a true there. The rest of them would be falses. Good. All right. Good. I'm glad your guys' PyTorch knowledge is still very fresh. All right, so similar things that you could do with C. C, you could use another tensor. You could use the tensor B to define which rows and columns you want to index. So same thing as in NumPy, effectively. B just basically, B in dimension 0 simply means only look at row 2, which means only look at this row and take all the values from this row. Makes sense. D is saying pretty much exactly the same. This is just sort of a comparison. Okay, makes sense. So lots of NumPy slicing is always very interesting. There's a select group of Python programmers that insist on writing code in as few lines as possible, and it's always interesting to see the slices some people come up with. And of course, well, even looking at is B a view of A? No, right? It's two totally different things. This is true, false. A is just a whole bit. B is definitely not a view of A. Is C a view of A? No, it's not. That's actually kind of an interesting thing. C is not a view of A, mainly because the compiler doesn't always optimize perfectly. You're using a variable that effectively could be random to index another tensor, and it does not like that. The compiler does not like optimizing based on runtime values. So usually it doesn't create a view. It creates a new array. But of course, D is a view of A. Okay, for that reason. This is a deterministic thing. The compiler has an easier time slicing based on deterministic values than other arrays, which could be any value. this is, I personally think this is likely to change. This is likely to change probably by the time of PyTorch 3, but who knows? Currently, that's what it does. Okay, let's see. Checking for all multiples of 7. That seems pretty simple. We just do exactly what we did before. We just take A, check if the modulus of 7 is equal to 0, print B, and then we get a new tensor B. That's just trues and falses. And then we could use this new tensor B to index A to get a new array like this. So getting all the multiples of 7. Yeah, all the good fun slicing. So yeah, use views whenever possible, which PyTorch tries to help you with. But of course, knowing how these slices work and knowing how slices are represented, that always helps you to optimize PyTorch also. Okay, compiler isn't perfect. You do have to rely on your own intuition a lot of the time. Okay, how much time do we have? What do you guys think? You guys want to try a couple of these? Or do you want to move on to the next topic? Yeah? You want to try? Let's try this. Let's try some of these quickly. How will we extract every third row, every third element of the last row? And let's say x is right here. So I could write here. I could write below this. Oops. Oh, well, I gave it away. Okay, every third element of the last row. you take the last row, you take every third element. Okay, why not B? I know why this happened. Issue with this rise setting. Okay, how about we just do extract every multiple of 9? How will we do that? Does anyone want to give it a shot? Yeah, please.
The print,
Oh, actually, yeah. Why define a new thing? Yeah, print.
A, and then square brackets.
X, yep.
Okay, then square brackets x modulo 9 is equal to 0.
9 is equal to 0. Yeah, pretty much. Yep, exactly. Exactly on the money. Last one. Extract every perfect square. Ooh, I don't know what that is. Okay. Print x. Let's do that formatting. I wasn't thinking of it, but good. Extract every perfect square. I will give you a hint. There is a function, a torch function. Let's use the torch function, square root of x. That might be useful. Yeah.
Torch dot square root mod 1 is 0.
Yes, exactly. Okay, good. Torch dot square root mod 1 is equal to 0. Oh, perfect. What am I doing here?
Oh, 0.
Oh, 0. Oh, 0. Jesus. Yeah. Yeah. So perfect. Yeah, you don't usually. I can't remember the last time I modulus 1. So, oh, good. Okay, so that's fun. Indexing is always fun. That should be a fun midterm question, right? Okay, so now that we've beaten that indexing horse, let's move on to PyTorch functions. Okay, yeah, we have time. Good. So we talked about functions a little bit last lecture, remember? So again, we have all the basic mathematical functions in the tensor library. Again, it's pretty much mirrors NumPy almost exactly. The only real difference is that for several functions, we have that underscore that does in-place computations, or this exp, which returns a new tensor, right? So remember what this underscore means. And you also have trigonometric functions and all the sort of good functions. So if you have you can initialize a random variable, take the log, or take the log by returning a new tensor, or you could take the log by doing the tensor function. Both of them share the same. Both of them return the same value. Okay, so all that so hopefully makes sense. Same as NumPy. There's a useful function in for torch. I can't remember if it's in NumPy also. I have to check. But it's the where function, where you could make the value of one variable, where you could create a tensor that chooses between the values of two variables based off a particular condition. Okay, so the where function basically says, given this condition, either use the value from x for this particular element, or use the value from y for this particular element. So, for instance, in the example here, we want to make sure that all the values, that we have some random tensor x that has both positive and negative values, but we don't want negative values. We have a beef with negative values for some reason. So we basically just want to make sure that if x is positive, use that value in z. If x is negative, use the value from y in z. Okay, and then that works out pretty well. The function where is very useful in a lot of different machine learning activation functions. So that's why we're mentioning it here. So there are two. Okay, so I'm ahead of myself. Okay, so functions which are a part of the torch library are often, like basically standard functions, are often referred to as activation functions. So that doesn't include the basic math functions, but it includes a lot of different machine learning activation functions. For instance, rectified linear units is a activation function that is specific to the torch library, and it's because this function is used in a lot of machine learning applications. And again, all this function is basically, if the value x is greater than 0, use that value. If it's not greater than 0, then select 0. Right? This is important for a lot of machine learning nets that don't really want to use negative weights. Right? Same thing with sigmoid functions. I'm sure you guys have seen this one before. Sigmoid function, very standard torch function that appears in very standard torch function that appears in I can't think of any machine learning models it doesn't appear in. So basically you have this step function right here. So the step function, it comes up pretty much a lot in computer science. It comes up a lot. Actually, a lot of you are probably electrical engineers, right? So this comes up a lot in like amplifier designs and stuff like that. So yeah, you simply define the function, you call the function, you get the function pointer, and you simply plot it. Okay, makes sense. So this function goes between 0 and 1, because if x is negative, then this value goes to 0, and then you have 1 over 1. If x is positive, then this value becomes big, and then 1 plus some big number under 1 is equal to, it gets closer to 0, closer and closer to 0. So that's why. Okay, so, I said that reverse, but you guys probably are following. You guys understand what I'm saying. Yeah. So I think let's try to modify this sigmoid function. Let's just try to work on that. So the idea of the sigmoid function, we have this 0 point that is centered around 0.5, and we have we have both, people try to modify this function basically to both shift this 0.5 value. So for instance, if we want 0.5 probability at 5 instead of 0.5, that might be something we want to do. And we could also maybe want to stretch out the sigmoid so that it doesn't rise quite as rapidly as in this standard metric. Okay? So, any ideas for how we would do that? First, any ideas for how we would modify the sigmoid function where to include an argument tau where the sigmoid has a sharper transition for some values of tau and where it has a sharper transition for smaller values of tau and a stretch transition for larger values of tau. Any ideas for how you would modify this little mathematical function so that it stretches with tau? Yeah. Yeah. Yeah, so that's 1. So I could just put /frac. No, don't do that. Okay, fine. You're not going to be the cool ID. Okay. Okay, good. So that'll help us with the stretch. Any idea on how to shift it left or right by some value b? Yeah.
Just put parentheses around the x or where the tau would be, and then do that minus b.
Yeah, exactly. So minus /left minus b/right. There we go. Yeah, and so if we if we write the function a bit, okay, well, I guess I'll just zoom out. We could see that there we go. There we go. Thank you, Firefox. You can see that with those modifications, if we make tau small, the transition is sharper. If we make tau big, the transition is slower. If we make b small, the transition gets shifted over. If we make b big, the transition gets shifted right. Okay, makes sense, right? So that's actually the more generalized version of the sigmoid function that a lot of people use. But anyway, yeah, so that's the sigmoid function. So the sigmoid, there we go. Okay, so we could go. So many activation functions. And also to note, I mean, a lot of you are going to be looking up these activation functions on the internet. So one thing that I want to mention now that we'll get into later a bit more is that effectively there's a sub-library of the torch.nn library called torch.functional. And the functions, and both have implementations of the same functions. The only difference is that the torch.functional library has no inherent state. The torch.nn library, sorry, the torch.nn library has no inherent state. The torch.functional library has inherent states. It doesn't matter for these activation functions, see right here. But then if you go into different machine learning functions that we're going to discuss later on, like cross entropy, there will be a difference just in how you write your machine learning model. So just something to be aware of if you look up online for a different activation function. Just be aware that if you're using torch.nn or torch.nn.functional, okay? It just changes the syntax of what you're doing, and we're going to get into how a bit more. But for these particular activation functions, it doesn't matter because they don't have internal states or memories, so either one works pretty much exactly the same. So speaking of other activation functions, we got softmax, which I'm pretty sure everyone has heard of already. The idea behind softmax is simply to show that which come on, there we go. The idea behind softmax is simply that you have a probability for each for multiple outputs, and just to normalize that probability curve so that one output appears more probable than the rest. So for instance, we could do a softmax along dimension 0. So we could do a softmax along dimension 0. So for instance, we have quote unquote activations of negative 0.2806 and 0.333, and we could use softmax to determine to normalize it and say, okay, this value is more probable than this value, and so on. Okay. So this is usually a last layer. This is usually used in the last layer of many machine learning models, and it's simply there to sort of determine which output seems most probable. Because the one thing softmax does is normalize everything to be a sum of 1. Normalize each dimension to be a sum of 1. So kind of an interesting function there. Has a lot of practical applications. Okay, so the major reason why people tend to use softmax a lot over something like linear normalize is that negative values in x shouldn't give negative probabilities. In fact, if we're looking at simple magnitude of the issue, if we're looking at simply at the magnitude of x, that matters, right? And constant offsets, like straight constant offsets for all elements across the board, it doesn't matter to softmax. So it doesn't. So it only cares about the relative difference between variables, not what the actual value of the variables are, right? So it's just weighing the variables with respect to each other. And we'll get into more why softmax works when we discuss deep neural nets. And also, I would like to mention that there are people that are vehemently against softmax and view it and say there are better activation functions. I don't know, but these things all have. Someone always has to be a contrarian, right? But the major thing to remember is that for most deep neural nets, softmax is used, especially at the last layer of the model. Okay, so let's just start with, and we're going to start derivation. So what do we discuss? We discussed indexing and we discussed activation functions. We're going to begin. So we're going to sort of introduce derivations and computation graphs quickly, and then next week when we discuss linear algebra, we'll get into more of those two subjects, okay? And that'll be it for the lecture. So, derivations of basic functions. Derivations are important because if we want to train a model, we have to know how much changing the input of the model changes the output of a model, right? That's basically what the derivation tells us. If we have what the small change in input would do to the output. So, how do we do that? Well, there's the analytic approach, which the derivative of sine is cosine, and et cetera, et cetera. If we have all these rules, we can have all these rules memorized. But also there is the abstraction of that. The derivative of a function is simply equal to the limit as h equals 0 between two consecutive points of that function. Okay? So, for instance, the derivative of x squared is simply equal to a point, the slope between a point x plus h squared and the point x squared over the distance between these two, over the distance between the x values of the two, which is h. And then we could solve all that. We could do the math there. The limit as h goes to 0, which is, of course, 2x. Okay? And so that's how computers calculate their derivatives, right? They don't necessarily solve things analytically. They solve things numerically. Um, so there are some analytical methods that you could. There are some analytical ways to. So again, you have these sort of rules that we've all memorized to compute derivatives. But unless you're using SymPy, these rules are almost entirely irrelevant. The computer is using this function to compute the derivative Okay. And so, what if we have a composite function? For instance, as we're going to discuss more, a deep neural network is one activation function feeding into another activation function, feeding into another activation function, feeding into another activation function. So the output is going to be a composite of multiple activation functions, right? So how do we calculate the derivative of a composite function? Well, it's the simple chain rule, right? I'm sure all of you have taken Calc 1 or 2. So in order to compute the derivative of f of x by hand, we simply need to redefine each of these functions. We could abstract them by saying the innermost function is g of x is equal to x squared plus 1. H of g is equal to log g. K of h is equal to sine h, and so on and so forth. And then we would know that the derivative of f with respect to x is simply equal to the derivative of k with respect to h, the derivative of h with respect to g, the derivative of g with respect to x, right? And so dh and dh cancel out, dg, dg cancel out, and you're left with dk, which is sine, which is the outermost, dx, right? So you could do this fairly simple. df, d h, oof. So df dx is simply equal to all of this, okay? So not fun to calculate by hand, but still very doable, right? Okay. Now, it's very structured. So this can get very lengthy and timely to communicate, but the derivative is very structured. And what we could do, and this is structured because we did the decomposition, right? What's important here is that we do the decomposition and we simply numerically calculate each of the steps of the decomposition to get the change at the output or at f with respect to x, right? So we could very easily go and get the change in g with respect to x. We could calculate that numerically using the limit. Then knowing the change in g, we enter that in here. We could calculate the change in g with respect to h using that limit, and so on, okay? So this is what's called a forward pass. So this is what's called a forward pass. So we evaluate all the derivatives in the corresponding locations and multiply them together. We're going to go over some more examples of this next week. So we're going to go over that. But before we depart, I wanted to sort of get to the point where you can start messing around with activation functions in TensorFlow. And then there's a nice little software package in TensorFlow that there's a software concept called computation graphs. So again, let's look at the function f of x is equal to sine of log of x squared plus 1. So right now, we have to manually implement the derivative, right? Unless we're using a package like SymPy, but SymPy has its own issues that I won't get into. I've had a lot of experience with SymPy. If you want stories, I could give it to you. But you don't want to use SymPy. So usually, when you want the derivative of this, you would have to calculate out the derivative and implement it like so, right? Now, that's not a fun thing to do, both for the user and for the computer. In fact, it's not fun. So and especially not fun because if the function changes a little bit, we would have to recompute and re-implement everything again. So So the good thing is that really the core benefit of PyTorch and most auto differentiation tools is that they provide much more effective ways to compute the derivative of composite functions. Okay, so they do this using what's known as a computation graph. So what does a computation graph do? Well, let's first look at a piece of code for how we would compute the derivative of this. And so how will we compute the derivative of this composite function? Sorry, f of x sine of log of x squared plus 1. Well, we simply say x is a tensor. We simply set x to be a tensor, and we set these and we tell PyTorch that we want to calculate the gradient, i.e. we want to calculate the derivative with respect to x, right? So that x that requires gradient equals true. That's us warning PyTorch, hey, pay attention to x, pay attention to all the functions that end up using x, because we're going to need to calculate the gradients of those functions eventually. We're going to need to calculate how those functions change with respect to x at some point in the future. So I'm setting this true right now so that you could set your different structures the way you need to. Okay, and then we have the composite function. We have g is equal to x squared plus 1. We have h is equal to torch dot log g, and we have k that is equal to torch dot sine h. Okay, so what does this mean? So what do we do? So now we have basically a function that goes from x to k. Okay, and we know f is simply equal to k. I should have labeled k as f. Anyway, so we have a chain that goes from x to k, and we could do some interesting things. First, we could do a sanity check for ourselves and ask PyTorch to see which of these are leaf nodes, right? Because what we're doing is effectively formulating a graph. We're saying x is connected to g, g is connected to h, and h is connected to k. So PyTorch itself is keeping track of the different nodes, and it's telling itself, okay, these things are here, they form a graph where x is a leaf, and g, h, and k are nodes in that graph. Okay, so what we do next, And so what we do next is that we could also calculate the actual values of g. So we know that x is a tensor equal to 1, so we know that g is equal to 1 squared plus 1, so that would be 2. That makes sense. Then we got the log of 2, or the natural log of 2, I should say, which is 6.931. I hope that makes sense. I can't do natural logs off the top of my head. And the sine of that, which also is equal to 0.63. So all that makes sense. And now we could calculate the manual derivative. And now we want the derivative, right? So again, like we said before, we could calculate the derivative manually using this long function, which is, we could calculate the derivative at 1 manually using this long function, which is 0.7692. Or we could calculate it automatically, which is simply asking for x dot the gradient. And x dot the gradient would be equal to 0.7692. Okay? So that's a pretty cool little trick, right? Because we don't need to calculate all of this out. All we're doing is telling Torch, this tensor, make sure we keep track of the gradient. Anything based off this tensor, PyTorch creates a dependency graph based off it, and then when we ask it to calculate the gradient, bam, it does it. It calculates it so simply for us. Okay, so that's pretty neat. What's also neat is that there's a nice little package that lets you visualize this. So those connections between the functions, it's called a computation graph. And computation graph is actually not a commonly used term. Computation graph, if you need a textbook for a computation graph, I highly recommend the grokking text on deep learning. That has a chapter on computation graphs. By the way, if you want textbooks or anything, post on Piazza. I have lots of good book recommendations. So the question is there a way to visualize the computation graph? And there is a way specifically for torch.nn library. And simply what we do is, again, we define some composite function. So in this case, we define a softmax we define some composite function. We have different activation functions, and then we define some particular graph, which is, I guess, these three activation functions sequentially. And we define a input to the graph, a 5 by 7 input. And then if we close it, and if we could visualize it using a nice little utility called TensorBoard. And what you get through this visualization is the input and how PyTorch is actually creating a graph of the composite function. Okay, so you go from a input that is this is from an old version. That is 2 by 3. It was 2 by 3, but for 5 by 7, it would change to 5 by 7. Sorry about that. So you go from an input that is 5 by 7, and then for each of these, it tells you the dimensionality of the outputs, then the output dimensionality, and so on. So what's useful about this computation graph is that it allows you, in this case, it's not that special, right? You could have done this very easily by hand, but imagine you have a deep neural network. Imagine you have AlexNet that we talked about last time. You will see a computational graph of AlexNet very soon. Then if you have that computational graph, it lets you very easily view your deep learning model in a way that's visually appealing, and it would probably help you see some errors. And also, one last thing to note is that you could define a new module using functions that aren't part of Torch. I mean, the whole point of Torch is simply that you could use any activation function. So again, going back to our example of sine of log of x squared plus 1, we could go here and define a new activation function, which is simply g is equal to x squared plus 1, h is equal to log g, k is equal to sine of h. And we graph our net and write it to our file, and then we use TensorBoard to view our file, and like so, we get a new computation graph where we go from a particular input that's any of some particular size, and it tells us how the size changes as it goes on. Of course, all of these functions don't change the size of the tensor. That'll be coming up in the future. But the functions that do, we have the computation graph that goes to particular values, that goes G, H, K, and then to the output. Okay, so that's kind of neat, I think. And there's a lot of nuances that goes into this that, unfortunately, we don't have time for. But that's something to mess around with on your own time. And yeah, hopefully you guys enjoyed today's lecture. And we'll talk about, we'll start talking more about linear algebra next week and how to do it with PyTorch. All right, that's all I have for today. And yeah, have a good weekend, guys. Oh, yes. Yeah.
Weren't you going to show the computation graph of AlexNet?
I'm going to upload it. I was working on it for today, but there was a bug in it somewhere, so I'm going to upload it. And it's for the DeepNets lecture. It's definitely going to be for the DeepNet. It's going to be in the DeepNets lecture. But for this one, I was like, there's always a problem with lectures. Like if I try to show too much advanced stuff, then like it just confuses people. So like I have to constantly, I'm like, do I put this in? Like, because it's kind of neat, but then am I the only one that finds it neat and stuff like that? So I decided against it, but yeah.
So I just forgot what the syntax of why we need this -1 here.